Divergence and Curl, Part 2. In Part 1, we looked at three-dimensional divergence. We saw that three-dimensional divergence measures flux across a surface. It is the dot product of the del operator and the vector field. Divergence is a scalar-valued function and is equal to 0 if and only if the vector field is source-free. Before we leave divergence, I'd like to look at one more vector field. We start with the radial vector field, r, and let phi equal 1 over the magnitude of r. Find the associated gradient field, f. Well, the first component of f is found by taking the derivative with respect to x. And we get negative x over the magnitude of r to the third power. Likewise, we find g and h, the other two components of the vector field. So starting with the radial vector field, we define a new vector field to be the gradient of 1 over the magnitude of the radial vector field, r. And incidentally, we just discovered that the inverse square vector field found in gravitational or electrical fields has the potential function 1 over the magnitude of r. It's pretty interesting. Now let's find the divergence of the inverse square vector field. Well, this actually is not going to be too hard. If you go back and review theorem 15.8, it states that for a radial vector field of this form, the divergence is 3 minus p over the magnitude of r to the p power. Now, if p is equal to 3, you get 3 minus 3, or 0. So we get a 0 divergence. So the divergence of the square vector field is 0. It is the only radial field of this form with 0 divergence. Meaning what? Meaning that it is source-free. Okay. Let's switch now to curl. Let's study three-dimensional curl. While divergence is the dot product of the del operator and the vector field, curl is the cross product. So curl of f is the del operator crossed with f, or the determinant of this matrix. The curl of a vector field is a vector-valued function. If at every point in the region the curl is the 0 vector, then the vector field f is called irrotational. If I calculate out the determinant, I get another way to express the curl of the vector field. Now, here's an interesting piece. Look at the k component. Recall that g partial x minus f partial y is two-dimensional curl. It gave rotation in the xy plane. Now, g partial x minus f partial y appears in the k component of three-dimensional curl. At the point P, it gives the rotation of the vector field in a plane containing P and parallel to the xy plane. The other two components have similar meaning. The I component corresponds to the rotation of the vector field in a plane parallel to the YZ plane. And the J component of the curl corresponds to the rotation of the vector field in a plane parallel to the XZ plane. We're going to finish this video with just an example. I'd like to find the curl of this vector field. Well, I need to set up my determinant. Remember, when I find the determinant, remember that my J component will have a negative in front of it. Okay, my I component is negative 2y minus a negative 1. My J component is 2x minus 1. Remember, it has the negative in front of it. And my K component is 0 minus 0. So the cross product is 1 minus 2y, comma, 1 minus 2x, 0. And that is the curl of this vector field. So I just want to remind you before we finish up that in three-dimensional space, circulation is measured using curl, and curl is a vector-valued function, as opposed to divergence, which is a scalar-valued function. Okay, I'll see you again in part 3. Take care.